Hello all, in the previous video we looked at the Lagrange dual of a problem. Now if you're wondering why the Lagrange dual was constructed in the way it was and why we required lambda to be non-negative etc., this video should provide us with some intuition regarding the same by taking a look at the weak duality theorem, which is essentially an implication of the way in which the dual was defined. Let x tilde be any feasible solution, that is the one that belongs to calligraphic x, and satisfies gi of x tilde less than equal to 0 for all I from 1 to m, as well as hj of x tilde equal to 0 for all j from 1 to p. Likewise, let lambda tilde and nu tilde be dual feasible solutions, that is lambda tilde of I is greater than equal to 0 and lambda tilde comma nu tilde are in the domain of Q. Then the weak duality result says that f of x tilde is greater than or equal to q of lambda tilde comma nu tilde. That is, the primal objective is always greater than or equal to the dual objective regardless of where they are evaluated at. Indeed, since this inequality holds for all feasible primal and dual variables, it also holds for the primal optimum and the dual optimum solutions. In other words, if we tighten this inequality to the extent possible, we would obtain P is greater than equal to D. This result is known as the weak duality result and holds for all problems, convex or not. In fact, the result can be easily proved and draws from the definition of the dual problem. In other words, the dual problem is constructed in such a way so as to satisfy the weak duality condition. Let us look at the proof. We begin with writing the Lagrangian for some feasible x tilde, lambda tilde, nu tilde. The Lagrangian is written as earlier. Now let us try to upper and lower bound the Lagrangian. First observe that this term is 0 because since x tilde is assumed to be feasible, it satisfies the equality constraint. In the same way, gi of x tilde is less than equal to 0 while lambda tilde is greater than equal to 0, so the second term is non-positive. In other words, we are adding something negative to fx tilde, so the whole term can be upper bounded by f of x tilde. It can be seen that Lagrangian is in general greater than equal to its minimum over x in calligraphic x. Here we have only used the property of the minimization operation. Finally, the minimum of the Lagrangian over x in calligraphic x is nothing but the dual function evaluated at lambda tilde, nu tilde as per its definition. Chaining together these inequalities, we have the required weak duality result. Observe that we did not have to use any properties of the functions or constraints. Instead, we only used the feasibility of x tilde, lambda tilde and nu tilde and the definition of the dual function. Interestingly, although assigning infinity values to p when the problem was infeasible or unbounded was done for the sake of convention, the weak duality property does in fact hold for those extreme cases. For instance, if p is equal to minus infinity, that happens when primal problem is unbounded below, it follows from weak duality that d is equal to minus infinity, which means that the dual problem would be infeasible. The result would in fact follow even if we were not following the convention. To see that the inequality fx tilde is greater than or equal to q lambda tilde nu tilde can be tightened by making the left hand side f of x tilde arbitrary large negative number. A natural consequence of that is that the dual function can be upper bounded by a large negative number for all lambda tilde nu tilde. But the domain of Q was defined as all lambda comma nu such that Q was greater than minus infinity. In other words, for a problem where P is minus infinity, the domain of Q would be empty. Note that the converse is not true, but a similar result holds in the other direction by setting d equal to infinity. That is, if the dual problem is unbounded above, the primal would be infeasible. In algorithms that make use of primal dual methods, they actually check if the dual objective is growing too large and signal infeasibility of the primal problem in case it goes beyond some threshold, let's say 10 raised to power 16. So the convention of assigning infinity values that we have adopted is actually quite useful in practical. We look at a simple example of the application of weak duality. The example should also serve to demonstrate the various steps in the derivation of the dual problem if they are not clear. We consider the following problem. P is equal to minimize over x transpose wx, where x is a vector in Rn whose entries are either 1 or -1. And the matrix W is real symmetric. This is also called the partitioning problem and is clearly discrete and non-convex problem where the solution space consists of 2 raised to the power n points. Many of the algorithms in discrete optimization such as branch and bound actually work by upper and lower bounding the objective function and by systematically cutting down the solution space into progressively smaller regions. So how can the objective of this problem be upper and lower bounded? First, the upper bound is easy. Just take any feasible vector and evaluate the objective at that vector. By definition, that becomes the upper bound of the minimum value the objective can take, that is p. The lower bound can be obtained by using weak duality. To obtain the dual problem, we first write the constraints as xi square equal to 1 for I equal to 1 to n, so that it is in the standard form. Observe now that the problem has n equality constraints and no domain restrictions. Let us associate dual variable nu I with the ith constraint and collect those into the vector nu, which is in Rn. So nu I are the dual variables. Then the Lagrangian can be written as L of x comma nu equal to x transpose wx plus sum over I from 1 to n nu I xi square minus 1. We can write the second term in the standard quadratic form as x transpose diag of nu x. You can see this by writing it out and multiplying them. The last term can be written as minus 1 transpose nu, and the first term remains the same. Next, the dual function is given by the minimum of the Lagrangian with respect to x. When minimizing, observe that the term minus 1 transpose nu does not depend on x, so that can be taken out of the minimization. Rearranging the remaining terms, we get minimize over x, x transpose w plus diag nu into x. So as an aside, let us consider the minimum of x transpose ax with respect to x for an arbitrary a. Recall that if a is PSD, then x transpose ax is greater than or equal to 0 for any x. And in fact, x transpose ax equal to 0 for x equal to 0. So the minimum of x transpose ax equal to 0 whenever a is PSD and the minimum value is attained at x equal to 0. On the other hand, if a is not PSD, then the quantity x transpose ax is actually unbounded below. To see that, suppose that a has an eigenvalue minus gamma, where gamma is greater than 0, and the corresponding eigenvector u, so that au is equal to minus gamma u. Then simply choose x equal to alpha times u. Since au is equal to minus gamma u, it follows that x transpose ax is equal to minus alpha square gamma times u transpose u. You can see therefore that x transpose ax can be made arbitrarily large, negative, by choosing alpha arbitrarily large, irrespective of what gamma or u are. In other words, if we take x arbitrarily large in the direction of the negative eigenvector, then the objective function goes to minus infinity, making it unbounded below. So in summary, we can say that minimum of x transpose ax is 0 if a is PSD and minus infinity otherwise. Substituting the solution back into the problem, we see that the dual function is equal to minus 1 transpose nu when w plus diag nu is PSD and minus infinity otherwise. Recall that the domain of q was whenever q was greater than minus infinity. Therefore, the domain of q is given by the set of all nu such that w plus diag nu is PSD. Therefore, the dual problem is written as minimize minus 1 transpose nu subject to constraint w plus diag nu PSD. Finally, it remains to apply the weak duality result by finding a dual feasible point nu tilde. In other words, we need to find nu tilde such that w plus diag nu tilde is PSD. There may be many such vectors, but a simple one is that we choose nu I to be the negative of the smallest eigenvalue of w for all I is equal to 1 to n. In that case, the quantity w plus diag of nu tilde becomes w minus lambda min w times identity. If you recall the properties of eigenvalues, then you can see that the eigenvalues of w minus alpha I are equal to the eigenvalues of w minus alpha for any scalar alpha. So the smallest eigenvalue of w minus lambda min w into identity is exactly 0. In other words, the matrix w minus lambda min w is PSD, and hence nu I equal to minus lambda min w is a feasible dual solution. So substituting that solution, the dual function evaluates to n times lambda min of w, and the required lower bound is given by p greater than equal to n times lambda min of w. So in this problem, we have seen that the various complications may arise when we are applying weak duality. If you are unfamiliar with this kind of analysis, a little bit of practice might be required. In any case, remember that we need the minimum of the Lagrangian in closed form, and it is quite possible for the Lagrangian to be unbounded below for certain choice of dual variables that you must identify. So that's all for this video. We have seen the weak duality result. The next stop is the strong duality result that holds for a particular class of problems.